Hey guys, welcome back to Pop 'em Up Chem. It's lesson 1 of organic chemistry. It's that time. We're going to be looking at homologous series, functional groups, what they are, and it's going to be a good base for the rest of the unit. Let's get it. So, no refresh because you haven't done anything yet, but I really would recommend going over Unit 4 and 14, bonding, in particular your Lewis structures, covalent compounds. That's going to be really, really important for doing this unit. Now, this video is going to be split, so you can use it if you're an SL or a HL student. You just have to be aware that on the keywords here, the bolded functional groups are for HL only. But for SL, you still do need to identify benzene at the very least. So let's get to it then. So what do we mean when we say organic chemistry? So this is the chemistry of carbon-containing compounds. It's not that it doesn't have any fertilizer. And these compounds come in 3 main types. We have aliphatic compounds. These compounds are characterized by this straight chain of carbon. So carbon, 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 all in a row. We also have alicyclic organic compounds. So these compounds still obviously contain carbon because all of these are organic, but they're characterized by joining up with themselves. They are bonded, the chain reaches around and bonds to itself and forms a cycle, hence cyclic, and we form a ring structure. Lastly, we have aromatic compounds, which are not to be confused with alicyclic. They are characterized by this 6-ring carbon structure and alternate single and double bonds. And so the main difference that you'll see here, if you've gone back and had a look at Unit 4, is we have a difference in hybridization of the carbons in the aromatic and alicyclic. The aromatic can also be attached to larger R groups. That's just any longer carbon chain. In fact, that's usually the way it is. There are many aromatic compounds. This leads us to homologous series. So you can think of homologous series as a kind of family. They differ only in the length of their hydrocarbon chain. They share a general formula, chemical properties, and a functional group. Their chemical properties change with their length, so with their size, so their reactivity can change. However, they undergo very similar reactions and just change in how vigorously those reactions occur as they change in size. There are quite a few different homologous series, and here are a couple of examples. You've got alkanes, alkenes, and alcohols. So they share this general formula, and that's basically a way that we can work out the proportion of hydrogen to carbon or other atoms. So you'll see here for alkanes, we have CnH2n plus 2, and we can test that on butane. So if we do the calculation for C4, it checks out. Unsurprisingly, alkenes, we have CnH2n. We obviously don't have an alkene for 1 carbon because there has to be a double bond. And then for alcohols, we have CnH2n plus 1 OH. You could say it still has the 2n plus 2, but it's just written like this so we understand that it's an alcohol. Again, as I said before, the chemical properties will change with size, but the functional group and the general reactivity will remain the same within a homologous series. Okay, time for some questions. So, is this alicyclic, aliphatic, or aromatic? Pause the video. Pop 'em up! It is, of course, aliphatic. And the reason it is aliphatic is because you can see it does not join onto itself and there is no benzene ring. What about this molecule then? Pause the video. Give yourself a moment. Pop 'em up! This one, of course, aromatic because we have that benzene ring clearly visible. Lastly, what 3 things do homologous series share? Pause the video. Pop 'em up! That's right, it's the general formula, the chemical properties, and the functional group. So the next is not for your whiteboards, it's just for the next task. I want you to pause and just draw one compound, any compound that's a valid Lewis structure that is, that has the formula C4H8O. Just pause the video, give that a go. So here's one most of you probably won't have drawn, so I've just drawn cyclobutanol. I've got the 8 hydrogens, oxygen, and the 4 carbons. This is just an example. The point being is that just that formula isn't enough. You could have drawn any of these compounds. So there was 20 compounds you could have drawn here. And the point I'm making is that our molecular formula, even though it's better than an empirical formula, is still limited information. I drew this one, number 18. So we want to look at the different ways we can represent molecules. Now, we've already covered empirical and molecular formula in previous units, and we just want to familiarize ourselves with the others. So firstly, we have full structural formula, sometimes called displayed formula if you're revising online. And this shows all hydrogen and carbon atoms, and it shows all of the individual bonds to the atoms they are bonded to. This can be kind of condensed, well, not kind of condensed, it can be condensed into the structural formula where we can take each of these groups of hydrogens and carbons and bring them down, and here you have a condensed formula, which can be very useful if you're typing to use this kind of condensed structural formula and can be a lot quicker. Lastly, in terms of speeding the process up, we have skeletal or skeletal formula. Here, every vertices and end of a line represents a carbon atom, and unless it's double bonded, it's assumed that that carbon atom on the corner as such is saturated. So it's assumed that this little vertices here is a CH2 group, and if it's the end of a line, it's CH3, and if there are 2 lines, then it's a double bond, of course. And if we want to have another type of atom, a chlorine, an oxygen, or any other type of atom, we just simply have that line going to that atom. Here we have chloroethane. So if we draw chloroethane, there's the skeletal formula, and then above I'll draw the full structural formula. You can see the difference and the time savings you can get here. So usually this is used to draw big molecules to save a lot of time, and you'll actually find in your data booklet examples where this is used for things like heme structures, because those are massive molecules. And less a type of formula in itself and more a way to represent formulas is the 3D formula, which you'll be familiar with from Unit 4 and from Unit 3 as well if you're HL, where the wedges represent bonds that are coming out of the plane of the page or board or screen, and the dashes represent bonds going into or away from the plane of the screen or board. So although you won't need to define any of these specifically, you do really need to be aware of all of these types and what they're representing. So, little task for you. I just want you to pause the video, and you've got the 6 types of formula that I just described in the middle, numbered, and you've got 6 lettered descriptions, and I just want you to try and match the letters and the numbers up with their respective definitions and vice versa. Pause it and have a go. So hopefully you got those. Empirical formula was matched up with D, molecular with F, displayed A, structural C, skeletal B, and 3D E. So those are our types of formulas, and we've looked at homologous series, at least in definition. Now we want to describe all of these different homologous series and their functional groups. And you're going to do this in a set of research, otherwise it's just going to be me talking for a long time. So pay attention to what you need to focus on if you're HL, and pay attention to also primary, secondary, and quaternary. The task is fairly simple. You'll find in the files folder a table that you need to complete on all of these functional groups. And you need to go online and use online resources. Try and use reliable resources, of course, to go through and describe the functional formula polarity, the naming rules, give an example, describe the relative volatility, and then also give the relative solubility in water. You also need to make notes on primary, secondary, and quaternary, especially as it relates to alcohols and the halogenoalkanes. But just so you're not completely alone in doing that, let me go through the first line of the table just to show my expectations. This is what the table looks like if you open up the file. And I'm going to start with looking at the alkanes. So here, it's got the name of the functional group. So I'm going to want to put in my general formula. So that's CnH2n plus 2. I then would have done my research online and I would have found out that there would be no polarity for the alkanes. Their naming rules are easy. We simply add ANE to the end of the molecule's name. So an example of this, I'm just going to pick something quite simple, would be ethane, which is just 2 carbons. Remember, 2 gives us the prefix of eth, and it's an alkane, so it's going to be called ethane. Genius. Next, we're going to describe the relative volatility. Remember, volatility is the tendency of something to vaporize, turn into a vapor. And these are very volatile, but they do vary. And some theme that you're probably going to come across is that they vary, that as they get longer, as the chain length increases, we're going to get a decrease in volatility. Now, if you've gone back to your Unit 4 or you just remember Unit 4 really well, that will make complete sense to you. Why will it make complete sense? Well, if we're increasing the chain length, then we're increasing the molecular mass, which means we're increasing the number of electrons and therefore increasing our number of van der Waals forces between the molecules. Therefore, they're going to hold on to each other more and less likely to vaporize. And this will also mean that the boiling point is going to increase with the same trend. Now, lastly, when we're looking at the relative solubility in water, we see that alkanes have no solubility in water. But it's important when you're going down this to think about why alkanes might not be soluble in water, because it's going to be important to understanding why some of the other organic chemicals are more or less soluble in water. Again, reiterating the importance of your bonding understanding. So pause here, head off, and take some time to create this table. This is really going to be a reference for you as we go through the unit, so really make it in the kind of formatting that you're going to want to look at again and again, and something that's going to be informative for you to use as we go forward. So pause here, see you in a bit. Okay, so hopefully your table turned out something like this, or even nicer, hopefully, if you're going to be continually using it. So I just forgot to put the alkyne functional group general formula here, which is like the inverse of the alkane, if you like. It's 2n minus 2. So this is the first kind of page, if you like, and what we start to see is the importance of polar groups and how polar groups are affecting the volatility, the boiling point, and their reaction with water. And we can see the same as we carry on. We can see here with the ketones. Why is this? Well, again, with bonding, we know that oxygen is going to have those lone pairs. And if we've got oxygen and hydrogen connected, well, then we're going to form hydrogen bonding in the case of carboxylic acids, which is going to really lower the volatility and really increase those intermolecular interactions. So for the SL people, This is as far as you'll need to go, including the halogenoalkanes, being able to identify esters and name the halogenoalkanes, also being able to notice amines and also draw and identify simple benzene structures. Remember, that's our 6 rings with alternate single and double bonds. You can draw that with the common skeletal formula or with the displayed formula, whichever works for you, as long as you have alternate single and double bonds. That all counts as a benzene ring. So if you're SL, this kind of understanding will suffice. Just being able to identify these groups is good enough. For HL, there are going to be a few others, so that includes the amide groups. These can be a little bit tricky to draw, and you don't actually have to know how to name these, because you can see here we have hydrogen groups, and this hydrogen could be another CH3 group, another R group, and so could the other one. This allows there to be primary, secondary, and tertiary amines and amides, which means the naming of them can be particularly difficult, and so it's not included in the IB specification. So I think one of the easiest ways to think about amides is to compare them to that of carboxylic acids and esters. And instead of where we have the OH group, we have the NH2 group. And also where we think of the ester linkage, we have that CCN instead of CCO group. That might be helpful for some of you. Amines, again, do not need to name these, just need to be able to identify them, because there is actually multiple nomenclature systems depending on whether you're a biologist, depending on whether you studied chemistry in the last 20 years or so. The IB has removed those, so you don't have to name those. Nitrile compounds, these are very simple to name, using exactly the same nomenclature as our alkanes, and then just adding nitrile on the end. And then we have esters. These can be a little bit tricky to name, so we're going to save naming esters for more depth when we study esterification and condensation polymerization a little bit later in this unit. And don't worry too much about maybe specifically revising this table, but it should be an accompaniment to other work we're going to do as we carry on going through the unit, so that you become more familiar with these different functional groups and their reactivity. So let's go over the terms primary, secondary, tertiary, and quaternary. So this effectively refers to the number of carbons that the functional group is attached to. How many carbons is that attached to? So this carbon here, where the functional group, alcohol in this case, is attached to one other carbon, and so we call it primary. Now, I think you may be able to guess what secondary would be. We've still focused on the carbon that is attached to the functional group. That's this central carbon here is attached to, not there, but yes and yes. So we've got 2. That is a secondary compound. Tertiary, we can see and might guess that we're going to have 3 carbons bonded to the group that is attached to that functional group. Now, quaternary for alcohols can't exist, and the reason for that is quaternary is obviously 4, but we can't have 4 carbons attached to a carbon that is also simultaneously attached to some other functional group. That would break the octet rule. So in general, and we'll investigate this further in HL, we see a decrease in reactivity as we go from primary, secondary, all the way through to quaternary. Time for some questions then. First one, what type of carbon is the carbon colored blue? Pause. Pop 'em up! It is indeed quaternary. We can see that the carbon is bonded on all 4 sides. We can see it's got this bottom bond, side, and front and back are all bonded to carbon, so we have a quaternary carbon. Next question. What type is the carbon colored in green? Pause the video. Pop them up. That's right, we had a secondary carbon here. We can see that it's got 2 hydrogens and it's also bonded to a carbon on the other 2 bonds. So 2 bonds, secondary. Next question, what about the carbon colored orange? Pause the video. Pop them up. So as you can see, we've got a bit of a Lone Ranger on the end here, only connected to 1 other carbon, and so therefore it is primary. Okay, so let's assess those functional groups. What's the name of the functional group in this compound? Pause the video. Pop them up. It is indeed an alcohol. You can see from that OH group over on the right hand side. Okay, try your hand at this one then. Pause the video. Pop them up. So this one is an ester, but be careful if you're asked to circle an ester group, you've got to get that CCO group included. And don't think examiners don't know when you're trying to be vague with what you're circling. Don't include other hydrogens. This is the ester bond. What about this one then? Pause the video and give this one a try. Pop them up. This is indeed an alcohol. Don't get confused just by the ring structure. This is not a benzene ring. It doesn't have the alternate single double bonds required for that. It's just a cyclic alcohol. Try this one then. Pause the video. Pop them up. This one is indeed a carboxylic acid, that COOH group on the right hand side, sometimes written like this to indicate in condensed formula. What about this one? Pause. Pop them up. It is indeed an ester. So good, we've done it twice. Just wanted to remind you again how to circle the ester group there. What about in this compound? There are 2. Pause the video and pop them up. So hopefully you're able to see the carboxylic acid group at the top, the COOH group, and of course now we've got alternate single double bonds, so we also have the benzene ring, making this an aromatic compound. So for HL students, I want you to draw the functional group responsible for amides. Pause the video. Pop them up. So here your key feature is that C double bond O N. Now each R group here could represent any carbon length chain. You could have given an example here if we made the R with no dash a methyl group, and we made R double dash and R dash a hydrogen each, we would get the most simple amide just here. These R groups can be the same or they can be different, and just like with alcohols and halogenoalkanes, the more carbon chains that are attached to this nitrogen, we have primary, secondary and tertiary amides when there is the correct number of carbon chains. Okay, try this one then. Amines. Pause the video. Pop them up. So once again, with the amines and the nitrogen containing compounds, we have the ability to make primary, secondary and tertiary versions of these. So if we were going to draw an example, very simple one here, with the nitrogen center being connected to only 1 carbon chain and being connected to 2 hydrogens, we would have a primary amine in this case. Again, you do not need to be able to name amines and amides because of the complex nature of the naming systems that have to be in place when we're doing this. Okay, have a go at drawing a nitrile functional group. Pause the video and pop them up. So we have the characteristic C triple bond N. There would be a lone pair also on this nitrogen with any given particular R group. It could be a small R group, just like the methyl group in this example I'm drawing, or it could be a larger, more complicated R chain. Have a go for ethers. Pause the video. Pop those bad boys up. So ether, very, very simple group. These R groups can be symmetrical or they cannot. It could be two methyl groups, or it could be one methyl group or whatever and another different chain. There is very common for people to be confused between this and ester groups. So you have to make sure that with the ester group, you know that there would be a C double bond O on one of the adjacent carbons. Make sure you don't get confused between ethers and esters. I don't know why the gods of chemistry conspired against you making something that looks similar on paper, also sound, and looks so alike in words. So, what's next for you? Well, no more videos for this session, but make sure you rewatch, get your notes, and really delve into functional group, because that's something that's gonna keep coming up. There are some practice worksheets for you to get more familiar with this. Thanks for watching, guys. I hope you enjoyed the video. Like, subscribe, and as always, practice makes slightly better.